In this video, we will be going over radical expressions and functions. So recall that an exponential notation represents repeated multiplication of the same factor. So for example, 3 squared is the same as 3 times 3, which is just 9. And 2 to the 4th power is the same as 2 times 2 times 2 times 2, which equals 16. So in this section, we will study the opposite or inverse procedure, which is finding the root of the numbers. So we'll start with squares, and the reverse operation of squaring a number is finding the square root of a number. So the square root of 9 is 3 because 3 squared is equal to 9. And the square root of 25 is 5 because 5 squared equals 25. So in general, the number b is a square root of a number a if b squared is equal to a. And we use this symbol to denote the positive square root of a number, and this symbol is called the square root symbol or the radical sign. So this expression represents the square root of 25, where the number under this radical sign is called the radicand, and the entire expression is called a radical. And the square root of 25 is just 5. So let's try a couple of examples. We want to find each square root if possible. The square root of 100 is 10, since 10 squared is equal to 100. And then for this example, we will first take the square root of 16, which is 4, since 4 squared equals 16. And then we'll just place the negative in front of the 4. For the next example, the square root of 4 over 25 is equal to 2 over 5, since 2 over 5 squared equals 4 over 25. And for the next example, again, we want to simplify the radical first, so the square root of 81 over 49 is 9 over 7, since 9 over 7 squared equals 81 over 49. And then we just attach the negative in front of 9 over 7. And for square root of negative 9, we would need to ask ourselves, what number do we have to square to get negative 9? There's actually no such number, since 3 squared is positive 9, and negative 3 quantity squared is also positive 9. Therefore, the square root of negative 9 is not a real number. And for the last example, the square root of 0 is just 0, since 0 squared equals 0. Okay, so let's write down a few properties about radicands and square roots. If the radicand is a perfect square, then the square root is a rational number. And a rational number is just a number that can be written as a fraction of integers. So, for example, the square root of 16 equals 4, where 16 is considered a perfect square. And 4 is a rational number because it is an integer and can be written as a fraction of integers, as 4 over 1. The square root of 100 over 49 equals 10 over 7, where 100 over 49 is considered a perfect square. And 10 over 7 is a rational number because it is written as a fraction of integers. So the second property says that if the radicand is a negative number, then the square root is not a real number. So for example, the square root of negative 25 is not a real number since the radicand of the square root is a negative number. And then if the radicand is positive and not a perfect square, then the square root is an irrational number, meaning it cannot be written as a fraction of integers. So for example, the square root of 13, since 13 is not a perfect square, taking the square root of this on a calculator will give us an irrational number, which is a real number that has a non-repeating and a non-terminating decimal. Okay, let's go over some higher roots. So just like we can raise a real number to powers other than 2, we can find higher roots of numbers, like these. This we read as the cube root of 8, and this as the fourth root of 81. And let's go over how we evaluate such roots. So for this example, in order to find the cube root of 125, we need to figure out which number cubed will give us the radicand of 125. That number is 5, so therefore the cube root of 125 is just 5. And for the next example, in order to find the fifth root of 32, we need to figure out which number raised to the fifth power will give us the radicand of 32. And that number is just 2. Therefore, the fifth root of 32 is 2. So let's generalize this. This symbol is read as the nth root of a, and if the nth root of a is equal to b, then that means that b to the n power is equal to the radicand a. And we call n the index of the radical. So as a side note, the regular square root has an index of 2, even though we don't actually write it in. So if there's no index, we automatically understand it to be an index of 2. Okay, so now let's talk about if the index is an odd number. If the index is an odd number, like the following, we can actually evaluate it even if the radicand is a negative number. So let's try a few examples. To find the cube root of 27, we are looking for a number cubed that will equal 27. And that number will be 3, therefore the cube root of 27 is 3. And to find the cube root of negative 27, we are looking for a number cubed that will equal negative 27. And that number will be negative 3, since negative 3 quantity cubed equals negative 27. And to find the fourth root of 16, we are looking for a number raised to the fourth power that will equal 16. And that number will be 2, so therefore the fourth root of 16 equals 2. And finally, to find the fourth root of negative 16, we are looking for a number raised to the fourth power that will equal negative 16. However, this is not actually possible. An even power will always give us a positive value. Therefore, the fourth root of negative 16 is not a real number. So, as a useful guideline, if the index of a radical is even, as it is in the following, then the radicand must be non-negative for the root to be a real number. So the fourth root of 81 equals 3, but the fourth root of negative 81 is not a real number. And the same thing with the sixth root of 1 equals 1, but the sixth root of negative 1 is not a real number. Another property states that for any real number a, if we have the square root of a squared, this will just equal the absolute value of a. So for example, if we have the square root of 3 squared, this will just equal the absolute value of 3, which is just positive 3. And this is because if we simplify the radicand first, we get positive 9, and the square root of 9 is just positive 3. And then for this example, the square root of negative 3 quantity squared will equal the absolute value of negative 3, which is just positive 3. And again, this is because if we simplify the radicand first, we also get positive 9, and then the square root of positive 9 is just positive 3. Okay, so now let's talk about radical expressions with variables like square root of x, square root of 4x plus 1, and the cubed root of t minus 1. And we can also use function notation to represent radical expressions. Okay, so let's try an example. We want to find the following function values, if possible. For f of 64, this notation tells us to substitute 64 in for x in the function f of x. So we get the square root of 64, and this evaluates to 8. So f of 64 is equal to 8. For g of 7, we are substituting in 7 for x of the function g of x. So we get the square root of 2 times 7 minus 9, which simplifies to the square root of 5. And since 5 is not a perfect square, taking the square root of 5 on a calculator will give us an irrational number. Therefore, we can just leave it in exact form. So g of 7 is equal to the square root of 5. For f of negative 25, we are substituting in negative 25 into x for our function f of x. So we get the square root of negative 25. And again, our radicand cannot be negative when we have an even index. Therefore, f of negative 25 is not a real number. And for g of 3, we substitute 3 in for x in g of x. So we get the square root of 2 times 3 minus 9, which simplifies to the square root of negative 3. And since our radicand is a negative number when we have an even index, g of 3 is not a real number. Okay, so now let's talk about the domain for square root functions. So when the radicand of a square root or even root function is negative, the function is not a real number. Therefore, any value that makes the radicand negative is not in the domain of a square root function. So let's do a couple of examples where we determine the domain. So for example 5, we want to determine the domain for the square root function f of x. And for this function, the index of the root is even. Therefore, our radicand cannot be a negative number. The radicand must be greater than or equal to 0 in order to be a non-negative radicand. So we can express this as an inequality and set the radicand greater than or equal to 0. And our domain will just be the set of all values of x such that x is greater than or equal to 0. And written in interval notation, this will be from 0, including 0, so we use a bracket, up to positive infinity. And now to determine the domain of g of x, notice that the index of the root is also even. Therefore, our radicand cannot be a negative number. So we take the radicand and write it as an inequality so that it is greater than or equal to 0. Now we want to solve for x. And we get x is greater than or equal to 9 over 2. Therefore, our domain is the set of all values of x such that x is greater than or equal to 9 over 2. And in interval notation, this will be from 9 over 2, including 9 over 2, up to positive infinity. So, unlike square root functions, it is possible to evaluate cube root functions when the radicand is negative. Therefore, any real number may be substituted into a cube root function. And the domain for a cube root function will be the set of all real numbers, and we can write this in interval notation as negative infinity up to positive infinity. So the domain for f of x and g of x will be all real numbers since this is a cubed root.